Bismillahirrahmanirrahim. Today we will discuss a simple example of mathematical modeling, and this example is about regression analysis. So, what is regression? So, regression is an attempt to explain the variation in dependent variable using the variation in independent variable. Let's say on x-axis we have independent variable and on y-axis we have dependent variable. So what does this mean? This means that y depends on x. If there comes some variation in variable x, so that change also brings some change in variable y. So the change in variable y is dependent on variable x, but the x variable is independent. It has nothing to do with the variable y, although variable y is dependent on variable x. So in regression, we try to explain how these two are related, or what function can be used to explain the variation in variable y when there comes some variation in variable 1. So regression is thus an explanation of causation, like it is an explanation of cause. Okay, cause is x, and this cause affect variable y. So in regression we try to explain how variable y is related to variable x. Okay, now if the independent variable sufficiently explain the variation in the dependent variable, the model can be used for prediction. Okay, now for example, here we have some samples. Let's say this is variable x. So when the value of variable x is at this position, so the output or the value of variable y is here. Now when we consider this sample, so for this sample the x is here and the y is here. Similarly, let's say for this sample the value of the x variable is here, but the value for the y variable is here. Okay, so now in regression, we if we have a good regression model, then we can predict something. Let's say we have an observation at this position. Now from this model, if we have an accurate model, then for this observation we can predict the variable y, or the value of variable y. Okay, now simple linear regression model means that, let's say we have these samples, sample 1 2 3 4 5 6 7 8 9 10 11 and so on, and we say that let these for these sample we can consider this one line. Okay, that all the samples goes through this line. Okay, let's say we assume that this is the mathematical model that represent these samples. Okay, so the equation for this line is y prime is equal to b naught plus b1x plus minus e, means error. Now what is b naught and b1? So b naught is y intercept and b1 is the slope, and slope is equal to change in y divided by change in x. So this line is now our mathematical model for these observations. This means that these observation or this model can be represented through this line. Now again, what does this mean? This means that let's say for this sample the input is x and the y, the output is this one y. Okay, so this is the output and this x is the input. So when we put some value in this input x, so using this equation we get the value of y, and this is actually the error, because now this model says that the observation is here, although the observation is at this position. Similarly, for this observation, the model says that the observation is here, but the actual observation is at this position. So it means that this is the error of the model. Means that the although the model says that the observation is here, but the actual observation is at this position. Now at this point, the model position and the actual position is same. Similarly, at this position there is a slight error, but now at this position our model, these samples are represented through some linear model, and this model says that this point, according to the model, the point is here, but the actual point is here. So this is the difference is the error. Okay. Similarly, in this observation, the model prediction is here, but the actual point is here. So these are model error, but anyhow these all points can be very easily represented through this equation. Okay. And now from this equation we can also predict something. Now for example, let's say the value of x is somewhere here, so we can predict where this where should be the value of y. So using this equation we can predict the value of y for some other input x. Okay, we have this model, and although this model is created from these samples, but now we can use this model for any other input. Okay, so the output of regression is a function that predicts the dependent variable based upon values of the independent variable. Okay, now the value of y is dependent on independent variable x. If we have this x, so we can easily find the value of y. So simple regression fits a straight line to that data. Now when we say linear regression, so linear regression shows that the model is a linear line or a line equation, mathematical equation that represent line. So in simple scenario, a linear regression is a mathematical model which represent a line. Okay. Now the function will make a prediction for each observed data point. Let's say this black dot is observation and this red is prediction. Okay, so on the line there will be the model prediction, and the black dot is the actual observation. So the observation is denoted by y and the prediction is denoted by y prime. And now for each observation the variation can be described as y is actual observation and y prime is explained or prediction of the model, and this e is error. So the actual observation will be equal to the model prediction plus its error again. Now let's say we have this point, so the model observation will be here, and now this distance is the error. So the actual observation will be the model prediction plus minus the error. Here this is minus and here this is plus. Above the line it should be plus and below the line it should be minus. Okay, so this is for each observation the variation can be described as, this is the actual observation, yes, actual observation, this is the prediction, and this is the error. Okay, sum of square of error, what does this mean? This means that a least square regression select the line with the lowest total sum of squared prediction. Sum of square prediction, like for each observation the actual value minus the prediction value and square of that observation. So the square of the difference of this observation plus the square of the difference of this observation plus this plus and so on. So this is the summation, and when we calculate the square difference of all the errors, then this is called sum of square of error or SSE. Okay, the value is called the sum of square error or SSE. Okay, sum of square regression. So this is the same formula. Okay, but the sum of square regression is the sum of the square difference between the prediction for each observation and the population mean. Now here the difference is that instead of actual value, we consider the population mean. Now in the previous error criteria, we were differentiating this value from this one, and here we are taking difference of this point from this one, this point from this one, this point from this one, and in the previous we were taking the actual observation, but here we are taking the mean value. Okay, so this is the sum of square regression, and the previous was sum of square error. Okay, so this actually shows the difference between the prediction and the actual observation. Okay, and the value is called the sum of square error or SSE. This is the first one, and this is the SSR, sum of square regression. So this is SSR when we take the mean. Total sum of square, the total sum of square is equal to SSR plus SSE. SSR is the difference with the mean, and SSE is the difference with the difference between the actual observation and the predicted observation. Okay, now R square, the proportion of total variation SST, that is explained by the regression, is known as the coefficient of determination and is often referred to as R. Now R square is equal to SSR divided by SST. Okay, and SSR divided by SST is equal to SSR plus SSE. So this is called the coefficient of determination. The value of R square can range between 0 and 1, and the higher its value, the more accurate the regression model is. It is often referred to as percentage. Now from the value of this R, if it is close to 1, then this means that the model accurately predicts the observation, but if it is close to 0, then this means that the model prediction is not accurate. So this is very important value. Again, we should go back to this SSE. SSE is the sum of difference for all observation between the prediction value and the actual value. This is SSE, and SSR is the difference between the observed value and the population mean. So this is SSR, and now SSR plus SSE is equal to SST, or SST means the the total of the sum of square. So SST is equal to SSR plus SSE, and this is the coefficient, and again the range will be from 0 to 1, and when it is closer to 1, then this means that the model accurately predicts the model is closely representing the observation, and if it is close to 0, then this means that the error ratio is too much. Okay, we can perform regression analysis in SPSS or Excel. So in next recording, I will show you how Excel, how this regression analysis is performed in Excel. Thank you.